I just realized that we're still not done with the physical pendulum. So before I pick up that example, I just like to point out that one of the important ideas that we used in the last problem on the physical pendulum was the use of the idea of torque due to gravity, and I referred to problem 6.7 in the first edition of Klepner and Kolenko. Um, and just want to mention the page number. It's page number 247 in this first edition. So please read this example. The idea is that you can replace the torque due to gravity by a single force equal to the weight of the object acting at the center of mass. So if the total torque you want to calculate about the pivot, then about any point actually, you can calculate the torque due to a single force equal to the weight of the object and acting at the center of mass. Alright, so let's get on to the physical pendulum one more time. Now it seems I thought I had used everything that we knew, but apparently not. So there's still another nice and simple idea, that is conservation of energy. Now energy is conserved, in particular we can say conservation of mechanical energy. Energy is conserved in the absence of friction. So if we assume an ideal condition where there is no friction force, then we can use a powerful conservation principle, which is the conservation of mechanical energy, which is that the kinetic energy plus potential energy of the system remains a constant. That is initial kinetic energy plus potential energy of the system of particles, in this case a rigid scale, a rigid body, remains constant throughout the motion. And so we have done problems based on this. Just to get back to the most favorite problem ever, which we've been doing since probably many years, is you get a pendulum and it's, let's say, horizontal or any position, and then you leave it and the pendulum comes swinging down, and the question is, what is the velocity here? And I think this problem has been done so many times that, so basically in kinetic energy plus potential energy in position 1 is the kinetic energy plus potential energy in position 2, and this helps us to find out the velocity of the object. Now let me do it quickly. We can choose some state as the zero potential energy. Maybe I'll use this, or maybe I'll use this. Okay, so this can be the reference state. Where the potential energy is 0. So in position 1, then the potential energy is mgl. Kinetic energy is 0 in position 1, and this is equal to the kinetic energy half mv2 square plus the potential energy in the final position, which we take it as 0 because it's a reference state. And therefore we get very quickly the velocity of the object in position 2, that is 2gl root. Now this is quick, and we know the limitation, and I think it should be highlighted in red. The limitation is there is no information on time. Okay, no info on how long it took to get from there to here. So what we done in the previous example is that, look, we did everything with the Newton's laws and we are able to make accurate predictions, but the point is that there is a lot of calculation involved and hard work, but we get everything, we get all info. But if we are looking for specific quick information of things like the velocity at the bottom, then we have the powerful principle, and it's worth writing it down once again: conservation of energy. So obviously we can use conservation of energy in the system of particles in pretty much the same way. Now let's finish this. As it turns out that we don't know the formula for the energy, or let's say kinetic energy of an object in pure rotation. And now this turns out to be a worthwhile formula, and the time has come now to need this formula, because we need to know the formula for the kinetic energy of an object in pure rotation if we are supposed to use conservation of energy. Now this turns out to be easy, and it's good to draw a famous picture again, and maybe I'll do it in the next page. So here's the most okay, so we have some random object which we've been drawing it like a spanner, and so here is a spanner, and this we have chosen this axis as x and y, and the axis of rotation has been taken as the z-axis. So this is the axis of rotation, this is z-axis, and we picked up a particular point on this object. Let's call it m1, and what we realize is m1 undergoes a circular motion around the z-axis, bad circle, and let's say the radius is ρ1. That is the distance from the z-axis. That's the radius of the circle. Now, for an object in undergoing circular motion, which need not be uniform, the velocity is instant. Okay, let's say speed is equal to ρ1 into omega t mod, if you like. Right. So now, so v square is going to be ρ1 square omega square t at that instant. Okay, and this is v1. So what we are looking for is the total kinetic energy of the whole system. Okay, please note, kinetic energy of the whole system is the sum of the kinetic energies of each particle at that instant, and plus so on, plus half m n vn square. Now this turns out to be half m1 ρ1 square omega square t. I mean, we're using this result, plus half m2 ρ2 square omega square. Omega is the same for each particle, and it goes on all the way. And this, if I could use the space here, so the total kinetic energy, this by the way is the kinetic energy of the system. That's what we are gunning for, and this kinetic energy of the system then can be easily seen to be half omega at that instant square, and in the bracket you have a familiar quantity which we recognize very quickly as the moment of inertia, plus mn ρn square, and this is so neatly remembered and written as half I omega square t. And remember that this has a uncanny resemblance to kinetic energy of a single particle, which is half mv square. So m has been replaced with I, and v has been replaced with omega, and this is for pure rotation. So one more time, let's write this: kinetic energy of an object in pure rotation is equal to half I omega at that instant square. We're talking about the instantaneous kinetic energy. Right. So remember this formula, because we want to use the conservation of energy. to solve a problem that is often asked in tests and in the textbooks. So here we'll make up a problem. There's a scale which can pivot about some fixed point. So this is the edge axis, and if you leave the scale, it completely comes to the bottom position, and then of course moves ahead as well, but let's say that it falls to the bottom position and it's gaining angular velocity. There seems to be angular acceleration which is not constant. So it's a very complicated problem, but if somebody tells me, look, I'm willing to not worry about how much time it took, but can you just tell me what is the angular velocity at the lowermost position, let's say position B, and the angular velocity at the position A, the start position, is 0. So I just let go from rest and it swings all the way till the bottom, perhaps moves ahead, but so if I'm willing to attempt this problem if you say that there is no friction in the joints, maybe no friction anywhere. Okay, no energy loss due to friction implies no energy loss, no mechanical energy loss, and that means that energy is conserved, a great principle. Okay, so the way we do it is we look at the center of mass. We look at the center of mass and see how the center of mass changes. The center of mass is the position of the center of mass is going to decide the potential energy. So I'm going to choose this or this. Maybe I'll choose this as my reference for the potential energy, and the center of mass is what is going to decide what is the potential energy of the object, much like the previous problem. And now what we're going to do is, this is L by 2, so so we'll just write it: kinetic energy plus potential energy at A is equal to kinetic energy plus potential energy at B. And what we are saying is the kinetic energy at A is 0 plus the potential energy at A is mg, mind you, L by 2, okay, where L is the total length of the scale. The kinetic energy due to pure rotation is half I, which happens to be ml square by 3 into omega square, omega b square, plus the potential energy at B equal to 0. Now as you can see here, the only unknown is omega at B, and we can find that out. Okay, so I'm not doing the calculations. You can do the calculations on your own, but it is pretty much apparent that the only unknown is omega B, and we got the answer very fast. And it's worthwhile remembering that while we got the answer very fast because of a conservation principle, there is no info on time. So definitely, if you want time, you want more accurate predictions, we need to fall back on Newton's laws, which is basically what was there in the last video. And this is an example of the use of conservation of energy. So that sums up what are the things we need to learn. We need to use Newton's laws for detailed predictions, and this requires fairly detailed calculation powers. On the other hand, sometimes conservation laws may give you important partial information pretty quickly, but what is missing is information on time. Typically the kind of problems that come up here are based on finding omega t, the final velocity, things like that. You must have seen in the last chapter. Right. So now finally we get a chance to get to Atwood machine, and I just like to point out that um, regarding the Atwood machine, um, I have told you before that it's important for you to read the problem before you see my video. So it's on page number 254, Klepner and Kolenkov, first edition, and it's example 6.10. Now what I see now in the book is that Atwood machine has been solved with the help of Newton's laws, and we need to learn the use of Newton's laws in this particular problem. But you can also do this problem based on partial information based on energy considerations. Perhaps it is there somewhere else in the book or in the exercises, but you should always keep your eyes open to see what you can predict based on energy considerations, on whether it's applicable or no, though it's not there in the example 6.1, because example 6.1 is focused on making you learn Newton's laws with respect to the problem. So there is, once again, just to repeat, there is everything that you've learned. So there is Newton's laws, there is rotation. In fact, it is pure rotation of the pulley, pure rotation of the pulley. Then there are Newton's laws, there are free body diagrams, and there are constraints, just about everything. So do read it, and then I'll try to do it slowly in the next video.